In this video, we are going to cover the Wald estimator, which is just a special case of the instrumental variable estimator when we have a binary instrument. So let's consider a simple model. Y equals beta 0 plus beta 1 x plus u. And we have the usual problem of homogeneity, which is the expected u, knowing x, is different from 0. And we have z, which is an instrumental variable. So consider Z as a treatment, for instance. You give some drugs to a group and you don't give the drug to another group. So Z is either 0 or 1. And the covariance between Z and X is different from 0. And the covariance between Z and U should be 0. That's the definition of an instrument. We're going to define some notations. So let's consider n1, which is just the number. So let's consider n1, which is just the number of observations where z equal 1. So it's just the number of people in the treatment group. Then we have n0, which is the same when z equals 0. So the number of people who were in the control group, they didn't get the treatment. We're going to define y1, which is the average y in the treatment group. So it's just the sum of yi's for the I such that the z is 1. And we have y0, so y0 bar, which is the average y for the group where z equals 0. So for every I such that zi equals 0. Similarly for x, we have x1. So x1 bar is the average x in the treatment group. And x0, the average x for the control group. Now that we have this, what we want to show is that the estimator for binary instrumental variables that we'll call the Wald estimator is just y1 bar minus y0 bar over x1 bar minus x0 bar, which is a much more simple form than what we're used to for the binary instrumental, for the instrumental variable estimator. So to show that, let's start with the standard formula. Beta 1 IV is just the sum of z minus z bar times y minus y bar over the sum of z minus z bar times x minus x bar, and I can add the I for more clarity. We know that we can rewrite this formula as sum of zi times yi minus y bar, applying the formula that we covered in the very first video of this playlist. Similarly, at the bottom we have sum of zi times xi minus x bar. And we see we have very similar formula for the top part of the fraction and the bottom part. So I'm going to do some manipulation with the top part, and keep in mind that we can do exactly the same with the denominator. So for the top part, the sum of zi times yi minus y bar, I'm going just to distribute the z here, so I get sum of zi times yi minus, and then I'm going to split the sum of zi times y bar. Now, what is the sum of zi times yi? We know that zi is either 1 or 0. For the whole group where zi equals 0, we just have 0 times yi, which is a sum of 0. So this group disappears. And for the group where zi equals 1, we have 1 times yi, which is just yi. So what we have here is just the sum of the yi for the group, the treatment group, the group where z equals 1. So what is the sum of the yi for this treatment group? It's just the number of people in that group, and 1, times the average y in that group. Okay? And this is because y1 bar is 1 over n1 times sum of yi for this group, and here we have the sum of yi, so we have n1 times the average. Now I have minus. I can take the y bar out of the sum because it's a constant, doesn't depend on I. So I have y bar. And then I have the sum of the zi, which is a sum of zeros and 1. And how many 1 do I have? I just have n1 ones. So I can rewrite this as n1 times y1 bar minus y bar. So again, I have n1 times y1 bar, which is the average y for the treatment groups, minus y bar, which is the average y for the full sample, both the treatment and the control group. I want to decompose y bar. So y bar is just 1 over n, the sum of yi's. And I want to split it into two groups, so I have 1 over n times the sum of yi for the treatment group, so for the i's where such that zi equals 1, and plus the sum of the yi's for the group where z equals 0. So I have a definition for this. 1 over n, I can rename this n1 y1 bar. And I can rename the other part n0 y0 bar. Note, n0 equals n1, n0 is n, the total number of people, minus n1, the number of people in the treatment group. So I can rewrite this as 1 over n, n1 y1 bar, minus, and then I can get rid of the n0 and just have n minus n1 times y0 bar. So if we come back to our top part here, I see I have the y1 bar minus y bar. I'm going to substitute this new formula for the y bar into this formula. So I made a mistake here, of course it's plus. And now I'm going to substitute the y bar I just found here into this equation with the y bar, that's just the equation for the top part. So I'm going to write it, sum of zi times y1 times yi minus y bar. We found that it was n1 times y1 bar minus y bar. And now if I take the y bar I found and put it in this equation, I have n1 times y1 minus, and then I have n1 over n times y1 bar then I have minus and plus, so that's a minus, and I have n minus n1 over n times y0 bar. So what I can do here is I can actually add in front of the y1 bar n over n, doesn't change anything, it's 1, and I see that I have n minus n1 over n times y1 bar, and I also have n minus n1 over n times y0 bar. So this is n1, and then I factorize the n minus n1 over n out, n minus n1 over n, and in the parenthesis I just have y1 bar left minus y0 bar. So that was the top part. If we look at the bottom part here, we can apply exactly the same logic, and we get sum of zi times xi minus x bar equals n1 times n1 minus, times n minus n1 over n x1 bar minus x0 bar. So if I come back to my estimator, beta 1 IV, the top part is now n times n minus n1 over n times y1 bar minus y0 bar over n times n minus n1, here it's a n1 of course, over n x1 bar minus x0 bar. This simplifies, and I get what I wanted at the beginning, which is y1 bar minus y0 bar over x1 bar minus x0 bar. So if we look at the top part, we see that it's a difference for the y between the treatment group and the control group, and at the bottom is a difference between the x's, the average x between the treatment group and the control group. This gives us exactly the instrumental variable estimator.